we want the door shut? Well, happy Neutrino Day, everyone. My name is Deb Wolf, and I'm the Director for Education and Outreach here at Sanford Underground Research Facility. The Education and Outreach team is actually a partnership between Sanford Lab and Black Hills State University, and we are proud to represent that partnership. With me this morning is Taylor Lenz. Taylor, would you introduce yourself to us, please?
Absolutely. My name is Taylor, and I'm currently a student at Black Hills State University, and I'm working with SURF as one of their interns with the Education and Outreach program.
So Taylor, did you experience the storm last night?
I did. I did.
Yeah, so I was looking out my window, and as I was watching the storm come in, I had this weird question that popped into my head. And so I thought maybe you and I could discuss my wonder.
Sure.
So here's my wonder. Can you see wind?
That's a really good question. You know, I think you can see wind. When I was watching the storm last night through my window, I thought it was going to take the leaves all off the trees. I could definitely see the wind in that storm.
Huh, interesting. Hey, will you pull that slide up for us? So let's take a look at this picture. Do you see wind in this picture?
You know, I think I do. In the photo, you can see the dog's ears going in the direction of the wind. There's the kid with the kite who I'm sure feels the wind pulling on that kite. And like the storm last night, those trees are definitely blowing in the wind.
Huh. But you're not actually really seeing wind, are you? You're seeing the dog's ears. You're seeing the dog's ears. You're seeing the tree bend. You're seeing the kite. You might feel the pull, but I don't think you actually see wind.
Okay, so what you're saying is we're not seeing the wind itself, but the effect the wind has on the dog and the tree and the kite.
Yeah, absolutely.
Okay.
So here at Sanford Lab and scientists all over the place, they actually use direct evidence, but they also use something called indirect evidence. So when we looked at that wind, what we were actually seeing is indirect evidence of the wind doing something, moving the trees, blowing the dog's ears, but not actually seeing the wind itself.
Okay, so that kind of also sounds like gravity. We don't see gravity, but we see the effect the force has on things, like a ball. You drop it and you see gravity work. And even like planets and galaxies from millions of miles away, we can see the effect that gravity has on those too.
Yeah, and that's another example of indirect evidence. So for those of you that on Wednesday watched Becky and Owen, and they were studying static, and they had the balloons, and the balloons actually would move an aluminum can due to static. Well, again, we didn't see the static. We saw indirect evidence of static.
That's true.
Yeah. So here at Sanford Lab, we're studying matter. And one piece of matter that we've known about for a long, long time are atoms. There's a really good example of an experiment that was done many years ago to understand atoms. So let's pull that slide up, shall we? So a guy by the name of Ernest Rutherford was trying to figure out what an atom's internal structure looked like. And you absolutely can't see the inside. So he sent this beam of particles through gold foil atoms. And what he saw was almost all the particles went right on through. And from that, he decided that atoms are mostly empty space. He couldn't see the empty space, but the fact that these particles went right on through, he said, hey, atoms are mostly empty space. But did you notice that a couple of those particles actually bounced back. They must have hit something. Now, it didn't happen very often. So what Rutherford figured out from that is that in the atom, there's a tiny itty-bitty dense core called a nucleus. And a few of those particles actually hit that core. So no direct evidence of the nucleus, but indirect evidence. And there's lots and lots of other examples of indirect evidence helping us to understand atoms and protons and neutrons and electrons and all of those parts. And indirect evidence is super, super important. Taylor, I thought today maybe what we would do to give everybody an example of direct and indirect evidence is to look at something or study something that is invisible, that we don't see, but that we all know a lot about, and we can observe how the properties of this stuff work. We're going to take a look at air.
Absolutely. In fact, I think I have an experiment I'd like to show you. I think it's pretty cool, but I don't quite know how it works yet.
All right, I'm ready.
So over here, what we have is an empty aluminum can with just a little bit of water in the bottom, and it's sitting on top of a hot plate. Next to it, we've got a container full of water, and what I'm going to do is take this can and very quickly flip it and submerge just the opening in the water. Now, take a second and think about what you think might happen, and let's see if your predictions are correct.
Hey, can I do a 3, 2, 1 countdown?
Absolutely.
All right, I'm ready. Here we go. 3, 2, 1. Oh my goodness.
Is that what you think would happen? Let me
That's
get you a better view here.
Surprising. So for our audience, whether you are live or watching this later, what do you notice? What do you wonder? So I noticed a couple of things. I noticed that the hot plate was super hot. I noticed that steam was coming out before you flipped it over. I noticed there was a loud pop when you flipped it over. And then, of course, I noticed that the can just got like all crumpled up. So we need to explore a few things before we can really understand why that can got all crumpled up. And so to do this, we're going to talk about air and try to decide whether air is matter. And if we're going to do that, we need to define what matter is. So matter is anything that takes up space and has mass. So we're going to, again, do a couple of demonstrations to see if we can figure out, first of all, does air take up space? So now it's my turn. So I have an empty Gatorade bottle, and I have just a little piece of paper. And what I'm going to do is I'm going to put that little piece of paper right here at the mouth of the Gatorade bottle. And then I'm going to blow the piece of paper into the Gatorade bottle. So now I want you, again, to make a prediction. I've got this piece of paper in the mouth of the Gatorade bottle, and I'm going to blow. What's going to happen? Are you ready? Here we go. Wait a minute. Let me try that again. Piece of paper, mouth of the Gatorade bottle. I'm going to blow the piece of paper into the Gatorade bottle. Ready? I think I'm going to give up. I cannot get that piece of paper to blow into the Gatorade bottle, even though the Gatorade bottle is empty.
That's true.
I know.
All right.
You wanna try one?
I will.
Okay.
For this one, we're going to get some water involved again. We've got a tub of water here and a plastic cup with a paper towel in the bottom. Now right now the paper towel's dry, but I'm going to flip it over and stick it in the water as deep as I can. Now what do you think will happen with the paper towel once I get it into the water? All right, can you see in there? It's completely dry.
Do it one more time.
One more time?
Yeah.
All right, straight down. And it's still dry. So one of the reasons this happens is because air takes up space. And so here in this cup, it's not just a paper towel, it's also the air around it. And so when I flip it over and stick it in the water, there's still that mass of air that's between the paper towel and the water. And there's a similar reason why Deb's paper ball wouldn't go in to the empty bottle. The bottle's not really empty. It's got that mass of air inside of it, and so when she tries to blow in that piece of paper into the empty bottle, she's adding air and paper into it. And so that air and paper have to go out somewhere. And so that's why you can't blow it into the bottle.
So air definitely takes up space.
It does.
What about, does air have mass?
Air does have mass.
I think you should show that to us.
Absolutely. So these next two investigations we're going to look at, air has mass and creates pressure. So over here, we have another tub with a bottle of water and straw sticking out. And what I'm going to do is blow down into that straw with as much force as I can. So right now we have the water, the air, and the straw, and I'm about to add more air to it. So based on what we've talked about before, what is your prediction that's going to happen once I blow into that straw? Got it? All right. Oh, it sprayed me a little bit.
Hey, Taylor.
Yeah. Let me do it. Okay. Oh, wet up my nose a little bit. All right, thanks, Deb, for the help. All right, did you guys see what happened? I definitely felt what happened. When I blew into that bottle, it created more pressure with that air that I was adding to it. And so that pressure with the air on top of it forced down on the water. That water had to go somewhere, and the only other opening was that straw. So once I blew in, it came up and out the top.
And up your nose.
And up my nose a little bit.
All right, I've got another one. All right, I'm going to move everything out of the way so that we can see this one. So again, what we're doing here, I'm going to use this to dry this off real quick. What we want to do is we want to show that air has mass. So all I've got is a piece of newspaper, one flat piece of newspaper. And then this is just a painter's stir stick. And so what I'm going to do is turn this way. I'm going to put that painter's stir stick underneath this very, very light piece of newspaper. Now what I'm going to do is I'm going to karate chop the painter stick. What do you think is going to happen if I hit this pretty hard with just this light piece of newspaper holding down the painter stick? What's your prediction? For those of you that are not watching live, I think you should actually hit pause and talk about this one. What do you think is going to happen? All right, here we go. I got a karate chop. Sometimes I miss. So we'll hope for the best here. Here we go. 3, 2, 1. And it didn't work. We'll try that one more time. All right, I'm going to try that one more time. 3, 2, 1, karate chop. All right, this time you saw it. Did you see what happened? The piece of paper barely moved, and the stir stick, the paint stick, actually broke. How is that possible? Well, guess what? Air has mass. There was so much mass pushing down, just air pushing down. It held the piece of paper down, and the painter stick broke as a result. Okay?
You know what, Deb? I think all this discussion about air and mass and taking up space, I think I understand what happened with that can now.
Oh.
Yeah.
Okay.
So when we had the can sitting on the hot plate, the water inside, that little bit of water started to boil, and that boiling pushed all the air that was inside of the can out of it. And so then, because air has pressure and a mass, there was still that air outside in the room that was pushing on the can, but there was no mass on the inside. And so when I took it off the hot plate and I sealed off that opening into the water, all that mass from the air actually did crumple the can. And the reason why cans don't crumple when they're empty just in the air is it has that air inside pushing back out as well as air pushing from the outside.
Oh, so there was air in the can initially, pushing out, and air pushing in. But after we boiled the water, it pushed all the air out. Now there's no air inside to push out, and air actually crushed that can.
Absolutely.
Wow. So air is matter, and we know it is because it has both mass and volume. It has mass and it takes up space. And yet we never once saw the air. We just saw the effects of air.
We didn't.
So it's the indirect evidence. It's back to that indirect evidence. And so I thought I would take just a couple minutes then and talk about a couple of the experiments that are going on at Sanford Lab that are using, gathering, or will be gathering indirect evidence to try to understand some things that are really, really hard to study. So the first one is something called LBNF Dune. And so with LBNF Dune, we are in the early stages of building a giant detector. We want to study neutrinos, hence Neutrino Day. And neutrinos are really, really, really hard to study because they're so small. Now, to help you understand how small neutrinos are, we were talking earlier about atoms and how difficult it is to study atoms because they're so tiny. Well, get this. If I had an atom here and I had a neutrino here, and I wanted to make the neutrino big enough that I could see it, so it's the size of a grain of sand, okay? So here's my neutrino, here's my atom, and I'm going to blow them up in size at the same rate, right? So blowing them up, blowing them up, blowing them up until the neutrino is the size of a grain of sand. How big do you think our atom would be?
They're both particles.
Yep.
A grain of sand, maybe a grape?
Maybe a grape. So we decided an atom is bigger than, nope. You know that if we got a neutrino as big as a grain of sand, the atom would actually be all the way out to our sun. That's how much smaller a neutrino is even than an atom. And we generally in school say atoms are like the smallest thing ever. So we have to build this giant, giant detector underground to get away from all of the cosmic noise that's on the surface to try to study these itty-bitty tiny things called neutrinos. And the only way we're going to study them is with what kind of evidence? Indirect. Yeah. So the other experiment is LZ. And LZ is our dark matter experiment. We're trying to be the first to ever detect dark matter.
Deb, if no one's ever detected dark matter before, how do we even know it exists?
Indirect evidence. Yep, so there's actually quite a bit of evidence out in our universe that shows us that all of the matter that we know about, that we can detect, is, well, that like 80% of it is not the kind of matter we know about. So we're looking for this other stuff, this dark matter, and we call it dark matter because we don't really know anything about it yet. We know very, very little bit about it. But we're pretty sure it exists because indirect evidence tells us that it's gotta be there. And so our LZ, our Lux Zeppelin experiment, is going to be searching for dark matter, again in our underground. If you saw our Davis campus tour, the virtual tour this morning, you saw LZ being installed in our underground. So the search for dark matter is definitely a matter mystery that has yet to be solved. And the mystery of why matter exists at all is a matter mystery that we're working on here at Sanford Lab. So we're going to leave you today with a matter mystery for you to solve as well. And so what I'm going to do, and you're not going to like this because we're not going to give you the answer before we end today, but we're going to do a demonstration, and we want you to notice and wonder, and then come up with your explanation. So I'm going to move this a little bit forward so you can see this tank. Empty tank. And by the way, a magician might do something like this, but this is not magic. This is science, right? All right. So, and then I've got some bubble solution. So before I do anything else, I just want us to observe what happens when we blow some bubbles. So we blow a bunch of bubbles, and those bubbles sink. I'll do it one more time. Blow some bubbles. And hey, gravity works. All right, so now I'm going to try, and I'm going to blow some bubbles, and I'm going to try to get some of them to land in the tank. And we're going to see what happens. All right, here I go. I got to be able to do this right. Oh, there's one. Oh, it popped. Let's do one more. Can we see that? Can you all see that on camera, what's happening? Nice. So the bubbles go into the tank, and then they just sort of bounce. Huh. All right, but outside of the tank, the bubbles sink. So that, my friends, is the matter mystery that I want you to solve. So in closing, I want to thank you all for joining Taylor and I here today, and for joining us this week for our neutrino celebration and our mysteries about matter. I will be posting some links for all these different demonstrations on the website so that you can try them yourself. However, I'm not going to, at least initially, be posting what the explanation is for why our bubbles hovered. You can, however, if you want to, submit your explanation to our Facebook page. But if you know the answer already, don't spoil it for the rest of us. So thank you very much, and have a lovely weekend. Thanks, Taylor.
Thank you.